Okay, is it working? Can I start? Okay, then thank you. Good morning, everyone. Thank you for coming back, and I hope you had a good last evening and a good night's sleep, and are ready to hear a little bit about more and discuss a little bit more about chemistry. And so today we will be moving and doing more chemistry and more synthesis, and tomorrow then it will be all day photocatalysis. And so as we move along, today I would like to show you a little bit. We talked yesterday about chemistry of furans and where the furans are coming from. Let me tell you a little bit what type of chemistry can be done with this, and I use this and as an advertisement for my group. I will show you a little bit of the chemistry we have been developing in our group. So before we start, let me see if I can switch this. Let me see if you're still all with me. So there's a new number, and I could tell you something about or I can ask you something about my country. So maybe you can tell me what the capital of Germany is. Okay, so the system is working. Okay, you are all very well informed. So Berlin is the capital now. Before the wall came down, before the reunification of Germany, it was Bonn. But then that changed in the 90s. The reunification took place in 1989, and then they decided in Germany to do to switch this to Berlin. So I show you a map. And let me see if I can get the pointer to give you a little idea where I'm coming from. So here's Berlin. This is our capital. Has about 3 million people. Very often, if you come to Germany, you might fly into Frankfurt. So Frankfurt is southwest. And the other airport you sometimes fly into is Munich. So Munich is also a big city with 1.5 million people. And then just about an hour north, there is Regensburg. And I told you already, the university was built in the 70s, has a pretty new campus, but the city center itself is very old. It's World UNESCO Heritage Site. And so this is where I'm from, River Danube, very nice city. Let me ask you something. Again, if you compare now Regensburg with your capital, New Delhi, what do you think, how much bigger in terms of population is Delhi? Is it 10 times, 50 times, 100 times, 200 times bigger? Okay, I can see I have a few mixed answers here. I gave this question to you for a reason, and that is also related to chemistry, and that is that you need to take in information very, very carefully. And when you get information, sometimes maybe in the main paper, people make an introduction and they're referring to other work. Sometimes these statements which might be made referring to other works might not be entirely accurate. Sometimes because maybe the authors also have not read the paper so well. Sometimes because they want to make their study look in a better light. Also very often in the normal paper, not all the informations are given So always very carefully check the supporting information. Sometimes you might find discrepancies between the main paper and the supporting information, or the supporting information might have details which are really vital to understand and also to reproduce maybe a paper. And you see what I did here is I tricked you. I gave you incomplete information combined with the fact that the map I showed you is not a map which was taken by some German geographic institute. It was taken by the Regensburg tourist office. And so two things happened here. I tricked you in a way that, let me go back, that I told you that our capital, Berlin, has 3 million people. I told you that Munich has 1.3 million people. And then I showed you Regensburg. And of course, you did probably the right conclusion. You looked and said, oh, look at this. Munich is smaller. Regensburg looks almost as big or maybe as big as Berlin. And then you probably know that New Delhi has about 30 million people. And then one good estimation is that maybe Regensburg is 10 times smaller, or Delhi is 10 times bigger than Regensburg. The correct answer is it's 200 times bigger. And you see, this all came because I gave you incomplete, I never said how big Regensburg is, but I gave you information around this, which was misleading in combination that this map was taken by the Regensburg tourist office, and they wanted to make sure that everybody can find Regensburg on the map. And so they oversized this here. You see, this is something you find very often in papers as well. People say, we have an exceptional broad scope. Our reaction conditions are milder. Often not accurate statements. What does it really mean, milder? Some people say, oh, it's milder because I can do it at room temperature. But then you do a photocatalysis, you have to use light. So is light at room temperature milder than 60 degrees, but you don't need light, right? You really need to be careful, especially when it comes to judgment. And that is also what I say when we try to write papers, we try to make as little judgments as possible, right? Sometimes you say it's good yields. Some people might think it's a good yield is 80%. Some people think about a good yield of 50%, right? That's all judgmental, and you need, we all have to do this sometimes. We cannot always give the accurate numbers all the way through the paper, but you need to analyze information very, very carefully and look at different sources and recheck this, and in order not to draw wrong conclusions, right? And as I say, very deliberately, I tricked you here. And very deliberately also for the informations, I gave this 10 times bigger because I have drawn you to the 3 million which our capital Berlin has, and I thought you are going to make the same comparison. Okay, so much as a starter. I will do a small advertisement today. Combined, I show you a lot of chemistry which was developed by my group. And here you see a group picture of the current group. They were just about to go to one of our festivals. So you see especially some of our girls having the traditional clothes on, which we wear in Bavaria, and especially when we go to these summer festivals. Some of you might have met Victor. Victor stayed here 4 months in indoor for research stay. So again, thank you for making him feel welcome here. And then you can also see I have a number of students, PhD students from India. This is Sunaina. I will tell you probably during the photocatalysis lectures a little bit what she is doing. Pavitra, Mangesh is hiding here. Tirtha is a postdoc with an EU fellowship, but he's about to leave now. His stay is over. So I think I don't think I have missed anyone. So these are my co-workers from India in the moment. And as I said, I'm very, very happy. It's great people, and I really like to work with them. So I would like to tell you what we like to do with furans and pyrols. And another tagline I like to use for this is turning hay to gold. because this is really where the furans and pyrols, I haven't really talked about this, but you can convert a furan very easily into a pyrol. This is really where they come from. And this turning hay to gold is actually goes back to a publication which was published in 1865. Wow, that's a long time ago. And that was published by Jakob and Wilhelm Grimm. These names don't say anything to you, but they are very, very well known in Germany. And so the Grimm brothers, they published a paper where they said that this little guy here can turn hay into gold. And so that is the father of this girl here bragged to the king and said, you know, my daughter can spin hay into gold. And the king says, hey, that's pretty cool. So let's put her in a barn with a lot of hay. And then, of course, she couldn't do it. But then in the night, this little guy came. His name is Rumpelstilzchen. And he could do this. He could turn hay into gold. And so this way he could save the miller's daughter here. But then he also said, I want your firstborn son. And so all the story evolves. So it was a lot more than turning hay into gold. Of course, this is an interesting effect. That is a story which our government, before we had the euro, thought that is such a great story that they put the Brothers Grimm on our 1,000 D-Mark note, on a 1,000 D-Mark bill. This is like today, this would be making the cover of a journal, right? Here it was the cover on our money, on the biggest bill we have. 1,000 D-Mark was the biggest one which we would have. It's about 50,000 rupees. And then also Hollywood thought that is pretty cool. And so they made a movie out of this, about the Brothers Grimm and their publications. And so there was famous actors there. Matt Damon was in there, Anne Hathaway, and quite a number of people who were starring in this. So the publications of the Brothers Grimm, and of course you know it's not publications, it was all fairy tales, right? But these are very, very famous in Germany, and we as kids, we all read it. But let's think about this. And you are a chemist. Would you like to turn hay into gold? Right? I would ask you this, right? Is that something, and you don't need to answer if you don't want to. It's a hypothetical question, right? Would you like to turn hay into gold? We all like gold, especially for jewelry. That's what we used it for thousands of years. We use it for coins. More recently, of course, the big applications for gold are in microchips, right? There's, of course, it's a big thing. But if you think about this, would it really solve the problems of the world if we have unlimited sources of gold? We probably could make unlimited number of computer chips, but we would still not feed the world, right? We would still not having essential resources we need. And so, again, this is an answer. There's no right or wrong. You're right. In the current world, you would be rich, absolutely. But I would argue that what we are doing as chemists to make useful products which really benefit mankind are much more valuable. And we talked about this yesterday, right? Health, energy, food, right? This is all important for us. And so I think, again, you should be proud of yourself that you choose chemistry as a profession, because I believe that chemistry is really the solution to a lot of problems we have to solve in the future generation, your generation, to advance and keep the world a good and maybe hopefully even a better place than it is today. Okay, so very hypothetical. I'm going to tell you a little bit what we do with these furans and pyrols. Right? And you can see here, again, this is something we talked yesterday and we'll show you very briefly again in a moment. The hemicellulose can be degraded to pentoses, and then by acid catalysis, it falls into this wall of aromatic furans, right? And that is the driving force, the aromaticity here. And then you can convert the furans by, again, catalytic methodology into, by reduction into this alcohol, by oxidation into the acid. And if you treat this with ammonia, you can also change the furan into a pyrrole. And so that is something we believe is useful because it is produced in parallel. It's produced from agricultural waste. Still has problems in the way how we can produce it. The acid extraction, talked also about this yesterday briefly, it is a problem. It's mainly produced in China, and if you ask for a quote, we did this. We wanted to buy a ton of this alcohol, and we got a quote from China, and it was 1,500 euros, shipping and the barrel included. I thought that is great. I thought I'd do this because when you buy it from Aldrich, it's 30 euros per kilogram. It's still not a lot, but you can see already everything you buy from Aldrich, usually if you want to make an estimate how expensive really the production cost is, you have to divide at least by a factor of 10. So I thought that's pretty cool. I wanted to order this. My university would not let me. They said, you will never use, before you get retired, you will never use 1 ton of this compound. Right? I thought it's cool because I wanted to do some of the chemistry on big scale, but they said, buy it from Aldrich, buy a few kilos, that's also okay. So I will show you that you can convert these furans in quite a number of different types of building blocks. We already showed you briefly the cyclopentanols. I will show you what you can do with this. We'll also show you that you can do cyclopropionation chemistry, catalytic and asymmetric, and that is a very useful compound. I can show you also, will show you that you can rebuild these furans and pyrroles to 6-membered rings or even to 7-membered rings. And I will show you that you can make peroxides photochemically by inserting oxygen into the carbon-carbon bond. So I think quite a number of hopefully interesting chemistry where we can discuss catalysis with this. And so this is what I would like to do. And I show you also a few natural product syntheses, because that is also what we are doing. And you see everything which is in red and blue here ultimately comes from the furan. And so we are building together, and you see in some cases, this is a natural product we made. Essentially all the whole framework is essentially coming from these furan building blocks. So, and the modern spinning wheels we like to use for this is catalysis. I also briefly showed you that we do immobilized catalysts on magnetic nanoparticles so that we have magnetic versions of a lot of our catalysts. And we use photocatalysis, and in order to scale up, we also use flow chemistry because this allows you to run reactions in a continuous setup and scale them up by just letting the reaction run longer. So it's a very convenient way to do this, and we will also talk about this a little bit more. I would like to go back of the two reactions we already have seen. I showed you yesterday that this furan alcohol, you can convert in this livolinic acid, and you can, if you have later on time and interest, you can look again through the mechanism. It's essentially all protonation, reprotonation chemistry, and water elimination. But the interesting thing is, it's pH dependent. If you use a strong acid, you will end up with a livolinic acid, which is very useful. If you, as an acyclic building block, if you use a weak acid, you will end up with the hydroxycyclopentanone. It goes through the same intermediate, this and this is the same intermediate, but in difference, if you have a strong acid, you have additional water additions, and then the reaction takes the course to the livolinic acid. If you have a weak acid, then you run through this intermediate here, you can redraw so that you can see it's an enol, which can attack the activated carbonyl group and form a 5-membered ring here. And so this is what we do. This building block is the building block we use a lot. We talked yesterday about thermodynamic stability, and some people already, when we talked about how this reaction goes, so somebody already talked about aromaticity. So note that we are converting an aromatic starting material, which is like the thermodynamic sink when we produce the furans, here into compounds which are not aromatic any longer. And so have a look for a moment. We also said this is a reaction which has 100% atom economy. So the number of atoms in the furan alcohol are exactly the same atoms which we have in the hydroxycyclopentanone. Right? It's just a reshuffling of atoms. And so my question would be, if you should make an estimate, if that reaction should be thermodynamically going from the left to the right or from the right to the left, how would you do this? And clearly, I told you yesterday, we do this under conditions of high heat, right? We have heated this to 240 degrees. So that is clearly thermodynamic control. And so the question is, what would you think if this reaction from the furan molecule to the hydroxycyclopentanone, which is a one-to-one rearrangement, it just shuffles atoms around, is that thermodynamically favored or not? And here you have three answers. You can just maybe even guess, but then maybe you can tell me how you come to this, guess. Okay, so we have at least two answers. I can always see how many people answer, because we have the number of answers here. So in the ideal world, I would get 3, 6, 7, 10, 13, 14, 15, 16, 17, 18 answers. 9 answers, 50% yield. In the paper, I would write moderate, right? Let's see, 12 out of 18, well, now we're getting 66%. Now I would almost think about maybe write good, but this is already dangerous, because I had review comments who said, 66% is not really good, right? So give me a break here. 16, now we're talking, right? So that's very good. So it's interesting what you do. So what do you do? So the one thing you realize is aromatic stability. That is something which needs to be overcome. What would you think how much this is? How much is the aromatic stability of such a furan? Let's start with a benchmark. How much is it in benzene? And you can answer in kcal or you can answer in kjoule. I don't care, because I can recalculate it. Have any idea? Well, we'll make a guess. How much is aromatization stabilization in benzene? Sorry? 40? 36. 36 what? 36 kcal. See, this is always what I have to ask when I talk to the young people. If I would talk to my generation, we would all know it's kcal, right? The young generation, I need always to ask which kind of unit you're referring. 36, 35, pretty good. So that's about a third of a strong bond, right? Carbon-hydrogen bond around 100. Aromatization stabilization of benzene is about 35 kcal. What do you think it's with furan? Is it more or is it less? Yes. It's less. Very good, right? Because it's not, you see with benzene, I can draw these resonance structures where I shuffle the electrons around. I cannot do this with furan, right? It's more a localized system. And this is also the reason why you can do with furan a Diels-Alder reaction, for example, and with benzene, normally not, right? So absolutely. And so the furan stabilization energy is probably around 15 kcal, so it's a lot lower. So we do not have, like a benzene, we would have to overcome 35 in the furan, we have to only overcome about 15. And now the next thing we need to do, and I find this very helpful, you will hear later on, I'm not sure today or tomorrow, you will hear about computational chemistry. So you could go now to your computer and say, computer, please let me know you do the starting material. It's very nice because it's an isomerization, so you don't need to worry about adding additional things. So it's a very good example for looking at the computational chemistry. So you could do this. You could do this probably yourself very easily. You have, I don't know, do you have ChemDraw here and Chem3D? You could put the molecules into Chem3D and do an MNDO or an MM2 calculation, and it would give you the enthalpies. And so it would give you a guess about this. But you can also do it a little bit by hand, and that's what we also mentioned already yesterday. You can simply compare what types of bonds are changing. And if you look at this here, then what you're doing is you exchange one carbon-carbon double bond to one carbon-oxygen double bond. And you exchange one carbon-oxygen single bond to one carbon-carbon single bond, because this is now a cyclopentanone. This has one carbon-carbon bond more, but in return it has now a carbon-oxygen double bond, and here it had only a carbon-oxygen single bond. And so you need to compare this. And a carbon-oxygen double bond is about 40 kcal more stable than a carbon-carbon double bond. And the carbon-oxygen single bond is about only 4 or 5 kcal more stable than the carbon-carbon single bond. And so by going from a CC double bond to a CO double bond, you probably win at least 30 or so kcal, depends on the source where you look up the bond energies. And you're only losing, by changing the carbon-oxygen for the carbon-carbon bond, you're only losing 5. So you probably go downhill by reshuffling the bonds by about 30 kcal. And this is enough to overcome the aromatic stabilization. And so I will argue definitely that this, although I have to break the aromaticity, that this is a thermodynamically favored reaction. And that's something, if we talk about driving forces, you should remember that, of course, aromatization stability, and whenever you can form arenes, this is usually a very good driving force in chemistry. But making carbon groups, CO double bonds, is also an extremely strong driving force because the carbon-oxygen double bond is so stable. And we all know this because when we burn something, what do we get in the end? We get carbon dioxide, right? So we get 2 of these carbon-oxygen double bonds, and this is why we always have that thermodynamic driving force here in this reaction. And so that's very good, and I'm not sure if Dr. Sarkar will tell you a little bit more about dearomatizations, and I know some of you have this photochemical dearomatizations as projects in their PhD, and there it depends a lot. It becomes a lot harder if you do it on a benzene or if you do it on a heteroarene like a furan, and to do this type of chemistry. Okay, so again, I would suggest simply keep this in mind, that analyzing which bonds are changing is a very powerful tool to give you very quickly an idea about if your reaction should be favored or if it is not be favored. Still, it might not go, right? Because the kinetic barrier might be very, very high. Right? A very good example is like if you form from graphene, if you make diamonds, right? Again, the diamond is thermodynamically much more stable, but the activation barrier to go from graphene to diamonds is very, very high. Okay, so I told you about this is the compound you can be making, and we find that this is actually a pretty useful compound. I'm not going to tell you how we do this, but we can do the resolution. We are making it from the furan in a racemic way, but we can run a kinetic resolution to make these compounds enantiomerically pure in a very good way. And here's one strategy which we would apply, and especially since we were aware that such cyclopentanones, which have such side chains here, are very prominent drug molecules. And so this molecule down here, which has this abbreviation TEI9A26, this is actually in clinical phase 3 for anti-cancer. And so the one thing we can do here is, you see, of course, it's an alpha-beta unsaturated carbonyl compound, so that should undergo Michael additions, right? And we also could have asked you, but I think it's too easy, right? You can ask yourself always with an alpha-beta unsaturated enone, is it adding on the carbonyl group or is it doing the conjugate addition, right? And the typical thing is this is the hard center, this is the soft center. If you would use a Grignard compound alone, you would add on the carbonyl group. But if you do it in the presence of copper, you're forming the cuprate, and the cuprate is soft, and so it does the conjugate addition. And so this molecule is doing something, I think, very interesting. These type of molecules with a group which was not a Bohr group here, but a TMS group, these are very well known from prostaglandin synthesis. Noyori pioneered these type of molecules for the synthesis of prostaglandins. But there, this hydroxy group would stay. Now we have, by making a Bohr group, or PMP is a phenol, it's a paramethoxyphenol, this becomes a good leaving group. And this is doing something quite interesting. So we can do the conjugate addition. We have one stereocenter here. And now the conjugate addition takes place trans from this group. Makes sense, right? An O Bohr group, that's pretty big, right? So we are adding from the trans position here. So this is the reason this N-butyl group, which we are adding here, or the octyl group, which we are adding here, comes from the opposite side of this substituent. And then once we add this, if you shuffle around the electrons, I will draw this in here. See, if your nucleophile comes, you add here, and I can draw all this, you have formed a new enolate, right? The intermediate you have formed such an enolate. And so, of course, this enolate will undergo reactions with electrophiles. And so you can introduce a second side chain, which we do here, and the electrophile we are using is an aldehyde. And so the moment we do this, we are generating such an addition product. And now what we found is interesting and very useful for us is that this alcoholate is able to abstract to make the other enolate over here. It's abstracting this. This one gets protonated, makes the enolate over here, and this will throw out the leaving group. So we are regenerating the cyclopentanone here. Let me go back to the laser pointer. So we're regenerating the cyclopentanone here because we're eliminating this in the end. So this is a case where you have a stereocenter, you have the control from this stereocenter of the initial addition, and I'm not going to go into this one here. This goes by a Zimmermann-Trexler transition state that is also very well controlled here. But then you're losing the stereocenter by eliminating this group here. And so it's normally it would be a diastereoselective reaction if it would stay on the addition point here and this stereocenter would remain. But now, because we are losing the stereocenter, it's an enantioselective reaction. And it's also diastereoselective in the way that the nucleophile comes opposite from here, but then the electrophile comes opposite from the nucleophile. So it's a very well stereo-controlled reaction where you're setting 3 stereocenters and you're regenerating the cyclopentanone. And so we did this for a number of examples, and it gives you very, very pure products. We did this especially for this drug molecule here, which we could get with a virtually perfect enantioselectivity and diastereoselectivity. And just comparing the optical rotation, the purity of the geometric isomers and enantioselectivity was much higher of what was previously reported by other groups was previously reported in the literature. Here's another thing you can do. You can add nucleophiles. That's what we did here. We added a cuprate. But you can also add radicals. And this is something we need to talk today, probably start, maybe not, but at the latest tomorrow, when we talk about photoredox catalysis, we will talk a lot about radical chemistry. And also radicals have the very good property that they can add to double bonds. And depending on the radicals, we will also have to talk about the type of the radicals. But some radicals, like the radical, this diphenylmethylene radical, adds very, very well to alpha-beta unsaturated systems. And so we have been able to start with this molecule. And when we add the cuprate, we got this molecule. This is the reaction I just showed you. We are adding phenyl minus, and the EE stays. It's from 99%, and here we still have 99%. Now here we are adding this radical, and you can see that the EE drops from 99% to 96%. That might seem small. We talk about this in a moment. But also keep in mind, look at this. Here we are just adding a phenyl minus. Here we are adding a pretty large radical. Still, the selectivity goes down. And so my question would be, do you have a rationale? Can you explain why radical additions might not be as selective as an ionic addition? Right? The phenyl minus, the cuprate, that was ionic. And then in the second step, I added a radical, and why is this less selective? I can go back here. So here you see again the two reactions, and let me see, is this showing? Oops. Okay, I need to recheck my. So it should still be open. Okay, but I don't see, here it is. So let's see what your idea here is. No idea so far. Is it not working? Should work now. Yeah. Okay. Okay, so now we're getting more and more answers. Okay, so the one thing I didn't really have here on this slide is I didn't have the temperature that this was run. And you're absolutely right. This is by room temperature. This was by 0 degrees. So typically, as we all know, lower temperatures make reactions more selective. But the other aspect, which most of you liked here, is what we know as the Hammond postulate. And the Hammond postulate tells us something about early and late transition states. And radical reactions typically go through early transition states because they are very reactive intermediates. And so an early transition state means that the radical to the reacting center can still be very far away before it reaches the transition state. And so in this way, if this is my substrate and this has a substituent which would like to say, hey, I'm a substituent up here, please come from down, the radical is still very, very far away and might not feel this. In an ionic reaction, it's a later transition state that the substrate is much closer already with the reagent, and so it feels much more the influence of the stereocenters in there. And that is typically one of the reasons it's much harder to control diastereo and also enantioselectivity in radical and then especially in photoreactions. It is possible. I will show you examples for this, but it is generally more challenging. I showed you that we went, and as I say, we added a very big radical. The yield, the EE drop, was 99% in the starting material, and then it dropped to 96% EE. It sounds very little, but how much is it really? How much more selective is 99% EE against 96% EE, right? This is always the scale we are using when we do asymmetric reactions. Okay, here we go. See, I said yesterday, the younger generation cannot calculate any longer, but you do very well. You do this very good here. At least I should say, half of you is doing this very well, right? Okay, yeah. So 99% EE, what is it? That's 99.5 to 0.5, right? So that's 200 to 1. And 96% EE is 98 to 2. That's about 50 to 1. So we go from 200 to 1 to 50 to 1. So 99% EE is about 4 times more selective. So this is a very deceiving scale, right? It looks so little. You go from 90. If you would talk about a yield and you would say 96% yield, 99% yield, you would say that's probably operator, right? I had a good day. I had not such a good day, right? I did the workup very carefully, or maybe I lost something. I didn't do the distillation or chromatography so well. But the EE scale, especially if you reach 90% plus, is very deceiving, and that the selectivities change dramatically if you even just go up 1 or 2% of the EE value. And you see this here. You have 3%, it essentially looks like 3% EE, but you have gone from 50 to 1 to 200 to 1. Okay, so very good. So we are all aware of this. I'll show you one more example. I'll show you now an HIV protease inhibitor, which we synthesized by the radical addition to this cyclopentanone. And these radical, these type of cyclopentanes, which has such furan rings annulated, there are many natural products available here. And so that was a target structure which we thought we could make. And here is what we are doing. I show this to you in the overall reaction, and in the photocatalysis section we will talk about this more. You can generate radicals from carboxylic acids by oxidizing the carboxylate. So you have a CO2 minus, you take with the photocatalyst, you convert the carboxylate to its corresponding radical. All right, so you go from the carboxylate. It's a very typical way to make radicals by a 1 electron oxidation. And this is what this photocatalyst, we will see more about this when we really talk about photocatalysis, can do. And it will convert the carboxylic acid, the carboxylate, to the radical. And these radicals, such carboxyl radicals, will very rapidly eliminate carbon dioxide and make the radical, make an alkyl radical. And that is something which is very useful, because now again this alkyl radical can do the addition onto the enone system. And then, as I've shown you, overall, pretty much in the end, we are also, like in the ionic case, we are going to eliminate this group here. And after the addition, so we are forming, after the radical addition, we are reforming the cyclopentanone. And so what we have done here in addition, you see the types of carboxylic acids we have used. They have an extra nucleophile here. And so this nucleophile then can rebind into the cyclopentanone. And so you can get, in one step, you can, onto the cyclopentanone, you can form a new tetrahydrofuran ring onto the cyclopentanone moiety. And this is something we utilized, and this is something which worked very well. And this is then something we have used indeed to synthesize these type of protease inhibitors, which were not invented by us. They were invented by a group in the US, but by an Indian scientist, Professor Ghosh. I've never met him personally, but I think he's in Indiana University. He has invented that, but he is coming from India. And these are fantastic protease inhibitors. So look at this. This is the structure, and you see here is this ring system, which is very decisive, and we have been able to synthesize this, starting from an amino acid, making the radical. So we are making this radical, the radical adds. We are doing the elimination, and then this hydroxyl group will rebind again into the cyclopentanone. So in one step we are able to do this. And my co-workers, they were very eager to actually make the compound, because we could have stopped here. That would have accomplished the formal synthesis. But they said, hey, let's make it. And so they made both of these compounds. And look at these activities. Picomolar. That's amazing. Right? This is really, I've never, and then single-digit picomolar. Typically, when we evaluate drug activities, we are very happy when we are in the nanomolar range, and even double-digit nanomolar range. But single-digit nanomolar range is fantastic. But here we have single-digit picomolar. So that is amazing, and a really fantastic activity. See what has happened here. In the radical addition, now we are adding a smaller radical. We started here, I've written it, we started with 99% EE. We are now down to 86. It's DE now because we coupled in the end a second molecule here with the chiral amino acid. So that's why we go from EE to DE. But still, we go from 99 to 86. And in the other diastereomeric series, we go from 99 to 91. So now you suddenly see 99%, we talked about this just a moment, is 200 to 1, 91%, 90% EE is only 95 to 5 any longer. So now we are down to about 20 to 1. 86, we are down about 10 to 1. It's still very good selectivities, but it simply shows you again this idea that the radical goes through a early transition state, and they are not therefore influenced so much by that inducing center here. Okay, let me tell you about another dearomatization reaction, and that is something which we also like a lot, and I would like to talk with you some more. You can do a cyclopropionation on these furans, and you can do this. I show you in a moment the reagents you do. And you typically do this, and you will be getting ester groups here. You can also get two substituents here. This works very well, and you can make such bicyclic compounds in one step. And you can make a diastereos and enantioselective selective. And these are compounds which we feel are very, very useful in upgrading, making a more valuable compound from something as inexpensive as a furan. Because this molecule which you have here is of course chiral now, We start with an achiral furane, but it's of course chiral and has 3 stereocenters, so you have the opportunity for doing asymmetric further functionalizations. And it has a very distinct convex and a concave phase. That is, again, a concept which everybody should bear in mind, because we are making very often cycles. And if we have 2 cycles which are 5-5 or smaller, in our case we have 5-3. If we start having 6-membered rings, it's not so pronounced any longer. But 2 5-membered rings, I said yesterday also, 2 5-membered rings, you can only make a cis junction, you cannot make a trans junction. 5-5 and smaller has a very distinct convex and a concave phase. It's like a coffee cup, right? And if you do anything, let's say, to this double bond, it will come from the convex phase, because onto the concave phase, the reagents cannot reach. So any type of double bond functionalization will occur from the convex phase and will set 2 more stereocenters. So in 2 steps, from a very cheap furane molecule, you will be able to set 5 stereocenters in this reaction. I will also show you that you can make cyclopropanes itself, not bicyclics, because you can utilize this double bond in different ways. For example, you can cleave it by ozone, and then you get an aldehyde functionality and an alcohol and amine functionality, and you have monocyclic cyclopropanes. But you can also utilize the chemistry of an enol ether or an enamine, so you can introduce electrophiles here. And then again, one very important aspect of such cyclopropanes is that cyclopropanes which have a donor and an acceptor substituent, so the donor is an oxygen or nitrogen here, from depending if it's furane or pyrrole, and then we have an acceptor here on this 3-membered ring. So that donor-acceptor relation makes these type of makes the cyclopropane bond very easy to break, right? Because we are having the lone pair of our heteroatom here. If this goes in, and then this bond breaks to the acceptor, you see the negative charge is stabilized on the ester group, so you make essentially an enolate, and then the donor gives the lone pair to stabilize the carbocation, you go here. So that is a very broad, and many people have used all kinds of donor-acceptor substituted cyclopropanes in order to activate, to break a cyclopropane bond again. I will show you also a little bit about radical chemistry, that you can also break the other bond. And then actually a project which was a lot of fun in our group, but which I thought is very useful, is you can also break the central cyclopropane bond. And that is useful because you are expanding a furane into a pyran, or you're expanding a pyrrole into a piperidine. And there are not so many chiral pool compounds like piperidines and pyrroles available, and so that is very useful that you can start from a furane or a pyrrole in order to do this. So I will show you a number of these reactions. So here's the typical cyclopropionation we are running, and you can again ask yourself, is that thermodynamically favored or not? And if you look at this, we are using a diazoacetate, a diazoester. Could have drawn this, but I'm sure you have seen this already. Could have drawn this with the nitro group here as well, with the nitrogen group here. And so this very easily cleaves in the presence of metals. It cleaves off the nitrogen, and you get the reactivity of a carbene. If you do this in the presence of metals, it's probably not a free carbene. It is probably a metal carbenoid. Right? So the carbene gets stabilized by the metal, and this is why this is doing this so well. And so here we are able, again, to do a cyclopropionation. We are breaking the aromaticity, and moreover, we're making a very strained ring. So ring strain is another concept. So I said earlier, what drives reactions? Aromaticity drives reactions. Reshuffling bonds to make more stable bonds drives reactions. And ring strain, especially release of ring strain, is also a very strong driving force for reactions. Here we are putting in the ring strain. How much ring strain in a cyclopropane? Does anyone know? What are we talking? Give me a number. You see, there's always a thing. I don't know if you guys have oral examinations. In Germany, we have a lot of oral examinations. So if I ask the question, then there are two possibilities, and you don't know it. If you know it, it's an easy way, right? You give the answer, everybody is fine. If you don't know it, then there are two possibilities. I ask the question, and you look at me, and I look at you, and we look at us 5 minutes in silence, and then I decide you don't know it. But the alternative is that although you don't know it, you start engaging in a discussion. And you say, okay, so let's think about this. Should it have be a ring strain at all? Should a cyclopropane be ring strained? What would be your answer to this? Sorry? Yes, but why? You see, this is exactly the point. So you would say, yes, a cyclopropane should have ring strain. And then I, as the examiner, so now we're starting a dialogue. And I would say, why? Why is this? And what would be your answer? Why is this? The bond angle in C as in an sp3 carbon usually is how much? 109 degrees. It's a tetrahedral. And in a cyclopropane, 60 degrees. Hey, so we are bonding significantly the cyclopropane. So it makes perfect sense that the cyclopropane should have ring strain. And then you could say, but then the experiment must measure this. And I would be happy with that answer because I don't really believe in memorizing too many numbers. If you do chemistry like I do 30 years now, somehow I remember it, right? Okay, that's okay. But you see, you need to start a dialogue in such a situation and not just say, I don't know it and I could give a number, but maybe this number is wrong and so on. You need to start discussing. So cyclopropane ring strain is about 27 kcal per mole. That's quite a bit, right? It's not as much as the aromatic stabilization, which we talked in benzene of 35, but it's certainly more than the aromatic stabilization in furan. So we are breaking the aromatic furan, and we're making a 3-membered ring. So overall, this sounds pretty uphill. And this is the typical way what we are doing. We're using a high energy reagent because this reagent, when it forms the carbene, is losing nitrogen. And that's probably the most stable leaving group which we have on the planet. So this brings us the overall reactions downhill because we have a very exothermic step in there. And that is typically something which we do in chemistry. We use high energy reagents in order to make reactions going where from the normal starting material to the product, which might be thermodynamically unfavorable. And I will tell you tomorrow, the day after tomorrow, something about what we like to call, it's actually not even us who have coined that term, uphill catalysis. Because that is something, instead of using a high energy reagent, you can also use light excitation. And so if you want to do a thermodynamically unfavored reaction, this is my starting material, this is my product. If I want to go from here to here, so either I have to use a high energy reagent, but I can also use light to bring my starting material into an excited state. So now suddenly from this excited state to the product, it's downhill. But overall, you have driven a thermodynamic uphill reaction. And I think this is very attractive because if you can do this by light, by an earth-abundant energy source, you can drive reactions which should be thermodynamically not possible. And that is something I think is very, very exciting. That is one thing I believe future reactions and photocatalysis. In the moment, we are really happy that we can do a lot of photocatalytic reactions where we generate radicals and then do reactions. But I think this concept that you can actually use the light energy to reach a higher state from that state, a reaction to the product is exothermic, but from the starting material, look from the ground state, it would be endothermic. I think it's very attractive. It's a very important research direction. So look again what we are doing. So we are having here these very high energy compounds, diazoacetates. I tell you in a moment, but maybe you also know how to make these. We do this with a copper catalyst, and we do this with chiral ligands, and these are very famous chiral ligands which are used a lot for copper. Bisoxazoline ligands, pioneered by Dave Evans, Masamune, Pfalz, three chemists more or less at the same time, made these type of ligands, and they are very, very easy to make because essentially it's an acid chloride which you need to condense amino alcohol. And the amino alcohol, of course, chiral pool you can get from the amino acid. So it's from the amino alcohol and then condensing with the acid chloride. And we have an acid chloride which has two acid chloride functions. It's a single step, and you can make these type of ligands very easily. And then depending on the chiral groups you have here, you can have that's depending on the amino acid you use. Very inexpensive. It's valent. More expensive are the tubutyl lysine variants, but you can make these type of compound, these ligands, very nicely. And copper is coordinating very well with them, and then this way you can make a chiral metal carbene of this type. This will then add to the furane, and you see it's an asymmetric reaction because the carbene can attack the furane from the top, or it can attack it from the bottom, and this gives you enantiomers. And then in addition, the reaction is very diastereoselective. You see the ester group is on the same side like these hydrogens. And then it's also enantioselective, diaregoselective, that it reacts on this double bond, and if you have substituents here on the other side, it will react on this double bond. I could actually ask you why this is. All right, so you see, I choose now a furane which comes from these renewable resources. Okay, this I can need to remember that I cannot see this. So we are having the furane molecule here, which has the ester group here, and this gives you this stereochemistry and this regiochemistry, in that it adds to this double bond, and it does not add to this double bond. So what would be the concepts? Last question before the tea break. What would be the concepts you would like to use to explain this? Let's see if anything is coming up here. Anything coming up here? No. Zero answers so far. And again, you need to analyze these type of reactions, even if you don't know it, but I think some people are typing something, maybe it's not coming up. It's almost tea break. Okay, here you go. Sterically hindered. Very good. Let's see if something else is coming up. Hindrance, hindrance, hindrance. Very good. Okay, so you guys like steric. Here's one very important sentence you need to remember. Again, if you're getting asked, do you have oral exams? Or you will do everything is written? How is it? Do you have ever any oral exams at all? No. PhD defense in the end? That's oral, right? At the latest step. But sometimes even in a written exam you might do this. Whenever you get asked why is something, like why is the reaction taking place like this? Why is it doing this? The first sentence you want to write down is, there are steric or electronic reasons for this. You don't need to look at the problem. This is always a good start. Steric and electronic reasons. And then you start analyzing steric and electronic reasons. But the first sentence, that's always the concept how you want to approach this problem, is to say this. And so, let's see. Steric reasons. Very easy, right? This is a more sterically hindered double bond than this one. Absolutely. I would completely agree that this is going to do this. If you think about, the ester is electron deficient, makes this double bond electron deficient. But what does it mean? Does a carbene wants to react with an electron deficient or with an electron rich double bond? So I think it's very good analysis, whoever wrote this, saying this double bond is less electron rich than this one because I have a direct substitution by the inductive effect which might pull electrons. What about a carbene? Is that typically electrophilic or nucleophilic? And you have heard, probably both, you have heard about nucleophilic carbenes. But a carbene which you get from the diazo ester, which doesn't have any donor substituents on there, it's an electron deficient compound, right? Because it has only 6 electrons on carbon. So it is an electron deficient compound, and electron deficient compounds preferentially want to react with electron rich systems. So in this case we have both the steric argument as well as the electronic argument would make the prediction that you should get the reaction on this side. Why is the ester group oriented on the same phase like the hydrogens? What's the reason for this? Because the reaction is diastereoselective. We are not trying to explain the enantioselectivity, if the carbene has attacked from the top or if it has attacked from the bottom. But why is the ester group on the same side like the hydrogens? Sterically hindered. Now we need a little bit more details on sterically hindered. I go back and show you when we started, look at this. This is the product. And you see that the ester group is oriented on the convex phase of that bicyclic system, right? So we have the convex phase and we have the concave phase. So it's like this. And all the substituents have a very strong tendency, if there's a choice, that the larger substituents will go on the convex phase. Again, this is a very important concept to remember when you talk about stereoselective reactions, because very often we do functionalization on ring systems. And then if you have convex and concave phases, the driving force for putting substituents not into the concave phase is very, very high. And I will show you in the second hour, I will show you a pretty impressive example for this. Okay. Tea? Okay, guys, you all deserve some tea, right? For me, it's so much easier because I do all the talking, so I'm not falling asleep, right? You guys need to have a coffee. Okay, so then we make tea break and then we come back here.